Okay, so we've already looked at this. We've already looked at this circuit. Okay, we know where this comes from. Okay, so this is the equivalent circuit referred to the stator side. So this place we said can be broken into two parts, like two resistors in series, right? This place is R like 1 minus S all over S, and this place is just R. And we said this is what contributes to what the losses, which is the P slip. And this is where we get our mechanical power from. So this is where we get P mech from. So that is why P slip here is equal to what this resistance, right? Times what the current that is flowing here, which is what IR what squared, the square of the current. Then for the mechanical power, it is the resistance here, which is R 1 minus S all on S, right? Times what the square of the current flowing through it, which is what IR whole squared. Is that okay? Yes. And this here, when we wrote this as R, we wrote it in this form. We saw that now the frequency we are going to have here is going to be what the omega E frequency. I hope that makes sense. Okay. So if you have some input power over here, part of it is lost in the part of it is lost here. Okay, in the stator resistance. And that loss is what IR squared times what RS. Is that okay? Then the rest of the power known as the air gap power goes to the rotor. And the air gap power is given as VI or V1 I1 cos or theta R. Okay. Then what this power when it gets to the rotor, part of it is lost in the form of a P slip. And we said a P slip, I've already given you one of the formula for P slip. The other one is what? The P slip is given as S is given as V2 I2 cos or theta R, and V2 is equal to what? SV1. So from the first session we had, so then P should be equal to what? SV1 I1, because I1 is equal to I2. Okay, so V1 I1 cos what? Theta R. So then this P slip. So then P slip, the relation we have here is what? The Edgar power. So then P slip should be equal to what? S times what? The Edgar power. Okay. So that's why we would like to keep, we can't make this zero. Okay. And I've already explained why we can't make it zero. So then we keep this very low in order to keep our losses was very low. Okay. So to operate with good rotor efficiency, the S must be kept small because the losses depend on what? S. So then a variable frequency operation, if you want to change omega R, you must change omega E. So we know that slip is equal to omega E minus omega RM. Omega E is equal to what? Slip. Okay. So the machine has a rated slip, so S rated. Is that okay? If you want to reduce, if you want to reduce if we increase the voltage without increasing the frequency as well, we are going to increase what? The rotor speed, and this is going to be what? Constant. Is that okay? Because this the speed here depends on what? The voltage. So then if we change the voltage and we don't change the frequency, it's going to change this. So if we end up reducing omega R, okay, if we end up reducing omega R, then we are going to have what? Then we are going to have a certain slip S1, and this slip S1 is going to be greater than what? The slip over here with S. Is that okay? And if your slip is increasing, it means your losses are increasing. But another way we could control omega R is by controlling what? Is by controlling omega E. And this is a better way. So if we change the voltage and we change the frequency as well, we are going to change omega E and change omega R. And we can change them such that the slip will not change, even though it's like you are doing 5 minus 3 on what 5. Okay, so this will give you 2 out of 5. You can still change this as what, maybe 10 minus 6 divided by what 10, and this will still give you what 2 over what 5. So then even though you've changed the values, you've not changed what the sleep, and your losses will still be what the same. I hope you get it. So that's why we are saying that then a better way to change your rotor speed is by changing what the frequency, because this here is equal to what 2 pi times what 50. Is that okay? So then a change in these are constant, so a change, so times what f. So if you want to change this, you have to change what the frequency. I hope that makes sense. Okay, so this shows the magnetization of maybe a magnetic material. Is that okay? Yeah. So consider 5G. That's the air gap flux level. 5G is controlled by what the MMF. Okay. So what we are saying is a magnetomotive force MMF is equal to what phi s. Okay. The reluctance of the part is like it's a constant. So and this is also equal to what Ni. Is that okay? So phi s is equal to what Ni. The number of turns is constant. The reluctance is like it's constant. Okay, so that means the flux is proportional to what the current. Is that okay? So then if so current is proportional to flux, however you write it. Okay, so if I want to increase the flux, I need to what increase the current. Is that okay? Because the number of turns is what, the number of turns is constant. Okay, and the reluctance is constant. So that means a change in this will result in a change in this. So that's the magnetizing curve. So as I increase the MMF, so MMF, so this MMF is equal to this. So if I increase the MMF, because the reluctance is constant, it's going to increase this in order to balance out the equation. Is that okay? So it will be increasing until a certain point. Is that okay? So that means that if I want more flux, let me redraw this. So I have current IF and I have flux. Okay. So as I increase the current, I'm going to be what? Increasing the flux. Okay. Until a certain point, the core, the core of the motor will start saturating. Then if it starts saturating, you see that it's no more linear. Okay, it's no more linear. It's almost constant, but it's not constant. It's almost constant. So at that point, we said that what the ion has started was saturating. Is that okay? So that if if I let's assume initially, if I increase current by 2, the flux increases by 2. When it starts to saturate, I may increase the current by what 50, and the flux has just increased by what maybe 10, or maybe by 5. Is that okay? Because what it has saturated. So the ion saturated as Im, which is the magnetizing current, is increased above its rated what value. Is that okay? So that means there will be a large increase in Im. Will only give you what a small increase in what flux. So at this point, you can see when I've changed the current from this point up to this point, the flux has just increased by what this. Is that okay? So you can see here it's no more proportional. That's when you've increased the flux or the current above its what rated value. But we also know that torque, electromagnetic torque, is proportional to what the flux and proportional to what the rotor current. Is that okay? So then, if we want a very high torque, we can get a very high flux and a very high current, and that should give us what a high torque. But here's the case: we said that what the flux, continue increasing the IM, it gets to a point where the flux doesn't increase significantly. Okay, so that means you be increasing the current, and if you are increasing the current, that's more power, but the flux you are only getting what small. So that means you are going to have what a lot of losses in your system. Okay, so ideally we want to control 5G to be as large as possible. So what we do is that we have T proportional to phi IR. Okay, so then we are going to increase this to a large value, like at, and leave it at what its rated value. Is that okay? Because beyond its rated value, we get what this a disproportionate increase in what flux and what current. So ideally, we want to control 5G to be as large as possible. And as we increase 5G beyond its rated value, the ion will saturate. That is a very large increase in IM, the magnetizing current, gives only a small increase in what 5G, which is not good. So then we get a disproportionate increase in what IR squared losses due to what larger IM. Remember IS, the IS or the rated current is what is the is equal to what IM squared plus what IR squared. Is that okay? So then if you continue increasing this in the hope of, if you continue increasing IM in the hope of getting a high flux, and here's the case, it's no more increasing the flux significantly. It means this value here will keep increasing. Meanwhile, you are not getting a corresponding increase in this. Okay, and we saw that what the stator loss is equal to what this RS squared what times what RS. Okay, so that means you are going to be getting a lot of losses in your stator with just a very small flux being produced. Is that okay? And that is not worth it. So then, so we get a disproportionate increase in I. So your losses are increasing. Meanwhile your torque is not increasing significantly. Okay. So then, and this will also lead to harmonics in the AC current, causing what extra losses. Is that okay? Because if the harmonics, if you get harmonics means you are going to get what maybe if you have a second harmonic, a third harmonic, that means the frequency of the harmonic will be what uh, a certain multiple of what the fundamental. So if it's the second harmonic, then the frequency will be what 100 hertz for a 50 hertz fundamental. The third harmonic will have like what 150 hertz. Is that okay? And that component is going to have what, a harmonic voltage. If you have a harmonic voltage, it's going to produce a certain slip, and the slip will be what higher. If the slip is higher, that means even the rotor losses, what the p slip is going to what increase. Because if the slip increases, the p slip will increase, because the p slip is equal to what s times what pag. Is that okay? So the harmonics that will be introduced into the system will also cause what extra losses, and we also get extra losses in what ion. That's hysteresis, because hysteresis losses, I think hysteresis loss is proportional to the frequency, and eddy current is equal proportional to the square of the frequency. One of them either have interchanged it, or but one of them is proportional to what the frequency. The other one is proportional to the square of the frequency. Is that okay? So if you get harmonics, that means your what your ion losses are increasing, your copper losses are also increasing. So why variable voltage? So that's for so for okay, why variable voltage? So we therefore control 5G to be its rated value. So we increase IM. Okay, we increase IM until it gets to what? Its rated what? Its rate till we get the rated flux. Once we get to the rated flux, we don't increase IM anymore. We keep what? IM constant. And if we keep IM constant, we are keeping what? The the flux what? Constant. I hope you get it. Let me see if it's still recording. So we keep the flux constant. So the rated magnetizing current is usually much smaller than what the rated rotor torque, of course. Okay, so we said that what the rated current from the stator or flowing the stator is what Im squared plus what IR squared. Okay, but the rotor current component is far greater than what the Im. The Im is just for what magnetizing what the core. Is that okay? So then, since the magnetizing current is much smaller than the rotor current, this keeps the total stator current okay low. Okay, so if what this means is if this should have been of the same value or should have a value close to this, then our stator our stator current is going to be very high. But because this is far smaller than this, relatively our stator current will be what low. Okay, and then our is squared, rs loss will also be what lower. Okay, so a flux level at flux levels below the rated flux, more stator current is what required for a given torque. What we are saying is Te is proportional to what phi and what IR. Okay, if this flux is too high, we'll get what a disproportionate increase in what losses. Okay, the core will saturate. But if this one is too low as well, that means in order to get a significant torque, I IR has to be what very high. And if IR is very high, P slip is equal to what IR squared times what RR. So then if our flux is below the rated value, we will need what more rotor current to produce what a high electromagnetic torque. Then if that's the case, in increasing the IR, we are going to what increase what the P slip. That's the losses in the rotor. Is that okay? So then this gives the stator. Okay. So at flux levels below the rated flux, more stator current is required for a given torque. Of course, if we increase IR as well, remember from this place, if we increase IR, we are increasing what the stator current. That means we are increasing this value too as well. You get it? So then the trick is what to make sure what you increase what the flux to what the rated flux. Okay, then that's a high value. Then you have your IR. Therefore, increasing of copper loss and reducing the maximum torque capability of the drive. Okay, therefore, for most applications, it is desirable to what operate at a rated flux so that iron loss. Should I stop the recording? Use 19 minutes. Hmm? Okay, but I don't need to share my screen before. So, Okay. So therefore, for most applications, it is desirable to what operate at what rated flux. I didn't stop. Okay, so therefore, for most applications, it is desirable to what operate at what rated flux, so that the iron loss and the copper loss at rated current at what minimal. Okay, so I think I've already explained this point. IM must therefore be controlled to be what constant at all frequencies. Is that okay? So we are saying that we want to increase the flux, the flux to what the rated what flux. Then we have the rated current here too. That will give us what the rated torque. Is that okay? And we want this flux to be constant at all times, at all frequencies. If you change the frequency, we want this flux to be what? Constant. For this to happen, that means what is producing it must also be constant. And we know what is producing it is what? Im. And Im is equal to what? The Vm divided by what? Omega E Lm or Lo. Because if you draw your circuits this way, this is the equivalent circuit. You have Vs over here. This is Vm. Is that okay? So Vm should be equal to what? Im, which is the current passing through this, should be equal to the voltage across this divided by what? Its impedance. Is that okay? So Im is equal to this. So the magnitude of Im should be equal to the magnitude of Vm divided by what? This. Omega E what? Lm. Okay. Okay. So Lm is the the inductance of the magnetizing branch is constant. Then if it is constant, it means for Im to be constant, for Im to be constant, then Vm divided by omega E must be what? Constant. The fact that they must be constant does this fraction here must be constant doesn't mean that Vm should be constant and omega E should be constant. It means that if you are changing Vm, you should change omega E in the same proportion. Okay, so that if you do two times this, you should do what? Two times this. If you have this, you should have this. Is that okay? So that at all times Im will be what? Constant. Okay, so for the first we solved a question earlier where we applied on this principle. Okay, so then Vm must be controlled to be what? Proportional to what? Omega E. I hope now it has sunk in. Okay, so then let's look at something. At high values of Vm and omega E, the voltage drop across the stator resistance and the stator leakage inductance VRL is very small compared to what? Vm. Okay, so what we are saying is you have, okay, so we have this branch. So this is Vs. Okay, and the drop here is what? VRL. This place is Vm. Okay, that means the drop across this should also be what? Vm. I hope this makes sense. Okay, and now we are saying Im should is equal to Vm divided by omega A Lm. We want this to be constant. So we want this ratio to be constant for Im to be constant. But we know that Vs here, Vs should be equal to the vector sum of VRL plus what Vm. Okay. And we are saying that at a very high value, if Vm is far greater than VRL, then we can say Vs is equal to what? Vm. Is that okay? And at the point where you have Vm is to be very high, that means omega E should also be what? Very high in order to maintain what? In order to maintain this. Remember, this is kept at the rated value. Is that okay? So then we are saying at very high values of what? Vm and omega E, Vs should be equal to a Vm. That means VRL, the voltage drop across this and this, is what far smaller than what the one here. Okay, so then therefore Vm is approximately equal to what Vs, which is the applied stator what voltage. I hope this makes sense. So now let's look at something. Okay, so now we are saying Im is constant, right? And it's Vm divided by omega E Lm. So that means omega E Lm Im should be equal to a Vm. Okay, now this is constant, and this is also a constant. So I can say what K, a certain K times omega E should be equal to what? Vm. So that I can say that what then omega E is should be what proportional to Vm. That is at a very high value of Vs. Okay. Then if this is the case, then if I plot this, let's say this omega E, this is Vm, then at a very high value, okay, at a very high value, this should be what? This should be proportional. Like this should be proportional. So that if for our case, if this is 1 5 volts, maybe we are going to have like maybe 50 hertz over here. Is that okay? Yeah. But from so this is where the high value start from. Any part here is what any part here would not, because at that time VM will be small. So if VM is small, then VM is not approximately equal to what? Vs. Okay. That means VRL will be significant compared to what? VM. Okay, yeah. So and magnitude of Vs is controlled to be what? Proportional to what? Omega E. So that's how you get this graph over here. Okay, so okay. Then variable frequency control, that's applied voltage is proportional to a frequency. So as you change the applied voltage, you change what? The frequency. So above omega E rated, Vs is held at its rated value, resulting in what? Field weakening. So what we are saying is we want Im to remain or constant, Vm on what? Vm on omega E Lm. And we are saying at high values of Vm, this should be equal to what? Vs over what? Omega E Lm. Right? Okay. So we are saying that about you can't keep increasing these two forever. Okay. This one has its rated value. So then when you get to its rated value, so that's where you are going to have omega base. Okay. So at its rated value, so you have something like that at its rated value. In order for you to increase this further, you have to what? Weaken the field. So you have to reduce the flux. So you have to reduce the current, which is Im. Is that okay? So that's field weakening. We've already seen field within it earlier. Okay, then we now look at the instance where VM is very high. Then at low values of VM, okay, at low values of VM is not what, almost equal to VS, because at that point VRL will be what, significant. Okay, then if that happens, then this equation you can't say VS is approximately what VM or the other way around. Okay, so what happens is at low speed or frequency, you have to boost the voltage. Okay, still we want Vm over omega E to be what, constant. Okay, but Vs is now equal to what, VRL plus what, Vm. Is that okay? So then if we can get something to supply this VRL, then we can still have what, Vs is equal to what, Vm. Is that okay? So then we call it, we say that what, Vs has to be boosted to maintain what, a constant Vm on what, Ve. I hope that makes sense. But if something is able to supply the voltage drop here, then the supply voltage here should be equal to what, whatever we have over here. So then if you redraw the graph, so the graph we drew earlier, that's what we have here. So you have to, so this is a boost voltage. Then here with this high value of what, Vm, that one, it will be proportional to what, this. And if you want to increase the speed beyond this value, then you have to weaken the field. Okay. Hmm? No, I'm tired of stuff. Ish. Yeah, the thing is plenty. Okay. So we've already established this formula, right? If you remember, in the first part, we saw that T is what, proportional to what, omega slip. Is that okay? Because we saw T is equal to what? T is equal to 3 VI squared. Um, this times P times what? S omega E, all divided by what? Omega E squared. Omega E squared times what? R squared. Is that okay? Yes. Okay. Yeah, so we already seen this. So this formula is when our slip is very small, because actually there was supposed to be plus something here. But if the slip, and that the expression here has what, S square in it, and we said that at this point, at this place, the slip is very what, small, because this is increasing slip, this is increasing speed. Okay, this increasing slip, so the slip is 0 here and the slip is 1 here. So at this point where the slip is very small, okay, the becomes this. Okay, this is a constant, this is a constant. So yeah, so at a fixed frequency, this is a constant, this is a constant, this is a constant, this is a constant, this is will become a constant, this will become a constant. Then the only thing changing here is what, S omega E. Actually omega E is constant, the only thing that will be changing here is what, S. So S omega E is equal to what, W sleep. Then we say that what, at very low values of what, uh at very low values of what, S, TE is what, proportional to what, W sleep. And this W sleep is also equal to what, omega E minus what, omega R. Okay. So what happens? So what happens when we keep Im constant? That is, if we change the voltage and the frequency in the same proportion, what happens is that our this one doesn't change. Our torque speed characteristics doesn't change. The only thing that changes is what? It just keeps shifting. Is that okay? So you can see where this okay, let's take this and this. This is when you are using 25 hertz, 200 volts. So let's say here I am, let's assume LM is what? 1. So then IM here will be what? IM here will be what? VM. So let's assume VM is equal to VS. So this will be what? 200 divided by what? Um, 50 pi, right? Then here you have what? Here you are going to have what? 400 divided by what? 100 pi. And this will still be equal to 200 divided by what? 50 pi. Okay, so you can see Im is constant, the flux is constant. So then, if even though you've increased Vm and you've increased what? Omega E, this Im is still constant. So the only thing that will be happening is the graph will be what? Shifting. Okay, or the sleep at which the maximum occurs will be what? Shifting. For this one, the this one is going to occur here. The maximum torque is going to occur at what? This sleep. So maybe around 0.3. This one is going to occur around maybe 0.8. Is that okay? So they will just be shifting, but the maximum torque will be the same for all of them. Okay. So then, what we are the part we are interested in what is the linear portion over here. This portion, this portion, this portion. So if you just cut the top part and leave what we are interested in, this is going to give you this. Is that okay? Yes. So if we control Vs to be proportional to omega E, then we have constant flux operation at most speeds and a series of torque speed curves where each line represents a different what applied omega E. Okay, open loop voltage variable frequency controls. Sorry. Okay, so just look at this. This open loop. So because it's open loop, we are not measuring what the speed of the induction motor. It's open loop. So what we do is we request a certain speed. Let's say we want a certain rotor speed of, let's say it's 1,400 RPM. Okay, then this request for speed, which is let's say 1,400 RPM, will go through what? A rate of change limiter. Then this rate of change limiter is its output is going to be what? A certain omega E. Remember, we want to keep Im constant. Okay, even though we want to increase speed, we want to keep what? Im constant. So Im is what? Vm divided by what? Omega E Lm, right? So once we want 1,400 RPM, this is going to this will go through a rate of change limiter, and its output is going to be what? A certain omega what? Omega E. The omega E that will give us what? An omega what? R of what? 1,400 RPM. Then once we get this output, this omega E, which is the synchronous speed that will give us this rotor speed, will go through what? A variable voltage, a variable frequency what? Supply. Then we need to generate what? A certain function. Okay, so so we said this is equal to what? Vs divided by omega E Lm. Okay, so then uh, the the speed over here is taken by a certain function generator, and that function generator is going to what? Generate a certain Vs. Is that okay? so that IM will remain what constant, because VM will be, you've requested VM here, there should be a corresponding VS that will keep what VM constant. So that will be generated by what this function generator. Then it feeds that VS to what the variable voltage, variable frequency supply. Okay, then that is supplied to what the induction motor. So use the fact that the slip is small at rated torque. That's 4% at what 10 kilowatt, even less than 1% for what the 100 kilowatt motors. And omega E, so that means for a very small value of S, it means omega R is approximately equal to what omega E, but it is not equal to. Because once it's equal to, the slip will become zero. And if the slip becomes zero, the slip frequency will become what zero, and the torque will become what zero. So for an open loop control, there is no what speed feedback. We already saw that. Then dynamic responses are what slow, because we are not getting feedback. So we can't readily know the real time changes in what speed. Is that okay? Therefore, the machine may not be able to respond within a short period of time. So then we may have to include a rate of change limiter for the speed to prevent the slip S from what increasing beyond what its rated what value. High slip will cause what an overcurrent. So based on steady state equivalent circuits, based on it, does not take dynamic responses of what real motor into account. Speed draws by a small amount with what load. Okay, because if a machine is running at a certain speed, if you load it, this speed would reduce a bit. Is that okay? And if there is no how do you call it? If there is no feedback, you can't readily know this. Okay, you need something to give you feedback. Oh, the speed has reduced. Okay, so speed draws by a small amount with what load. Okay, that is up to the rated slip frequency. Garrison tire. So now for the closed loop speed control with slip compensation for variable frequency drive. This one incorporates a speed measurement and feedback. Okay, so it measures the speed of the induction motor and it gives feedback. And it works on the principle that torque is proportional to a slip frequency. That's TE is proportional to what? Omega slip. The derivation of this scheme is based on steady state analysis, which is not what valid under rapidly or changing condition. Okay, so this analysis or this assumption is based on our steady state analysis. Then that means it doesn't take what the transient analysis into consideration. So therefore, it may not give a good performance under what a dynamic performance, because if something changes, it has to go to what some transient state before what is steady. So let's take it, um, you are driving a car, then the car bumps into a hole, you are going to have some what oscillations. Okay, then as time goes on, it what dampens and reaches what is steady state. Is that okay? So that if this analysis doesn't take the transient state into consideration, maybe the percentage overshoot and all that, it doesn't take it into consideration, and it's only considering what the steady state, then its dynamic performance may be what poor, because you don't know what happens in the transient what state, or if something changes right now, you don't know how the motor will react to it. Okay, so more complex schemes based on full transient representation, that's differential equations, have been developed. These are known as what vector control schemes, and they achieve better. Okay, so this is how the closed loop look like. Initially, um, we didn't have this here. We didn't have the speed transducer, or maybe a tachometer or something. We didn't have them here, so we were not having any feedback going here. It was just this going straight into this. then this one going straight. Is that okay? So what happens is that there is a speed demand. Okay, then it measures the current speed, then that will give you what? A speed error. This speed error is fed to what? A PI controller with a limiter, and the output of this PI controller is what? A torque. Is that okay? Because if you want to increase speed, you need to what? You need more torque. Okay, so then the error here, or the actuating signal here, goes through the PI controller. Then its output is what? A torque demand. This torque demand times this proportional gain will give you what? W slip, because we said our Te is what? Proportional to what? Omega slip. So that means Te should be equal to a certain constant times what? Omega slip. So this here goes through what? A proportional gain, and that gives you what? Omega slip. Then you know omega r over here, right? Because we know that what? um SWE is equal to omega E minus what? Omega R, right? And this here is what? Omega slip. Is that so? Omega slip is equal to omega E minus what? Omega R. Okay, so that means omega E should be equal to what? Omega E should be equal to omega slip plus what? Omega R. Okay, so then we still want to keep Im constant. Is that okay? Constant. Therefore, even if we request a speed where we get a speed error over here, which goes to a PI controller with what? A limiter, it gives us what? A torque demand. This torque demand goes through a proportional gain and gives us what? A P slip. Then this slip frequency is compared to what? The rotor frequency. It added to it, and together that will give us what? That will give us the required omega E. That will give us what? Our required speed. Okay, then this omega E goes to what? A function generator, and generates what? The corresponding Vs. That will give us what? Im to be constant. Then these two parameters are fed to the variable voltage, variable what? Frequency. So that means I'm changing Vm, and I'm changing what? Omega E, and I want my Im to be constant. Okay, yeah, so that's the closed loop. Six, seven. Okay, so practical realization of variable voltage, variable frequency supply. It uses pulse width modulation to create what? Variable voltage. It uses a pulse width modulation to create um, variable AC voltage from a fixed DC voltage. Okay, that's the DC link. They have high frequency switching, whatever. Okay, yeah. So this is what it's talking about. Okay, so let's assume in Ghana here you have a three-phase induction motor that you want to control. You want to control, right? You want to control the speed by controlling the voltage and controlling the frequency. Okay, the three-phase voltage coming has what? A fixed frequency of what? 50 hertz, and its uh, phase its phase value is what? 240 volts. Its line voltage is what? 415 volts. Okay, these values are fixed. Okay, but here's the case: you want to what? Be able to change the frequency. Then what do? There is nothing that like can just take the AC signal like this, without changing it to DC and just change the frequency. No. Okay. So what happens is you have an inverter, you have converters, power electronics converters. Okay. So what they do is they will first of all take this AC and they rectify it into DC. So when they rectify it into DC, they now have DC. So it's like you have a rectifier connected to what? An inverter. Is that okay? So you feed the rectifier with the AC. Then the question is, I have AC and I still want to supply AC to my machine. Why do I have to rectify it? Yes, because you want what? A variable voltage and a variable what? Frequency. And that's the only way you can do it. So what first of all you connect your three phase to what? The rectifier. Then this rectifier is going to rectify uh, the voltage or the current, whatever it is, the voltage into what? DC. Okay. Then this DC voltage is fed to what? This DC voltage is fed to what? An inverter. Okay. Then in the inverter, using a pulse width modulation, you are able to what? Modulate this. You are able to use um you are able to change the frequency and what? The magnitude of what? The voltage. So it's like you have AC, you convert it to DC, then you now convert this DC to what? You now form an AC from what? This DC. In the process of forming an AC from this DC, you what? You change the frequency. Okay, so it's like you have DC and you are producing and AC from it. Okay, so this is a rectifier part. So these are diode rectifiers. Okay, then these diode rectifiers, there's an inductance here. So the inductance here ensures that what the current is what? Smooth, because it won't allow the current passing through it to change instantaneously. Then you have capacitors over here. So this is a capacitor. The capacitor here is to ensure that what the voltage is what? Smooth. Okay, because when this one is increasing, will be storing or charges. Then if it's reducing, this one is going to what? Dissipate the energy it has stored. Okay, so then you rectify it. After rectifying it, you now invert it. So this is the inverter part. Okay, so this is the inverter part, and this was the rectifier part of it. Okay, yeah. So this is your DC link. So rectifier, inverter, and this your DC link. You know. So voltage source inverter or voltage fed inverter or variable frequency variable voltage supply. The front end is what? A diode rectifier. That means the inductor helps protecting what? During startup. And it's okay. So what this means is when you are starting this machine, when you are starting this machine, it draws what? Very high current. And the other job that this inductor does here is that it limits what? The inrush current, because it won't allow the current to change, the current passing through it to what? Change instantaneously. So it's going to cause the current, like, okay, it's like you can't change through me, or you can't just move from 0 to 100 through me. Like you have to convince me. You get it? So it will cause it to what? To be moving small, exactly. So then it helps in what? Limiting the current. Is that okay? Because of the fact that it doesn't allow current to change. Inductor doesn't allow the current through it to change instantaneously. Okay. So then the inductor helps protect during what? Startup. That means it limits what? The inrush current. The inductor also helps limit current during or shoot through. Yeah. So um actually, shoot through. Okay, you've done power electronics, so you know shoot through. Shoot through is where you have two. Is it one during changeover? Okay, sometimes a diode is not a diode that's supposed to go off before another one comes on is not totally what on. It's not totally completely off. Then the one that's coming on has already come on. Then that's going to create what a short circuit. Is that okay? Then if it creates a short circuit, that means a very high current is going to flow. And it's the job of this inductor to what? Limit that current, okay, during the shoot through. So yeah, that is shoot through. Okay. So the capacitors act as what? Energy store to provide high frequency current or harmonics. Okay. Okay, yeah. So this the pulse width modulator is connected to the gate of these devices over here. Okay, so the pulse width is what regulates the switching of or the switches you have over here. So I think this one is just for I think one phase, right? That is just for one phase. This is for the three phase. So you have three legs. Okay. Yeah. So these are the switching sequences of the switches. Yep. Okay. So you've done most of this in power electronics. Okay. It's already past 4. I'll see if I get another time. I'll do the rest and solve the rest of the question with you. These ones are not plenty. Well, our time is up and we'll continue later. Thank you.